Okay, this one's interesting. The fundamental theorem of calculus, part 2. And pay attention here. I will say one of the more abstract things that we do in calculus. You'll see in a minute. The process isn't that challenging, but it's just the concept. Like, okay, you got to really trust what it's doing, because you're not going to be able to get a physical value all the time. So you got to trust what the theorem is doing here. It's a little bit abstract. Basically, it boils down to this. As normal, we need a function that's continuous. It could be an open interval this time, or just an open interval I. And there's two equivalent ways to say it. I'm going to just go to this one. So this is one way to say it. But equivalent, here's the other one. Here's what it says, d dx, so the derivative of your integral from a to x of f of t dt equals f of x. So kind of in words, it says doing the derivative of a function with respect to x. Doing the derivative, but it's of an integral of the function. So derivative of the integral will replace the function with whatever variable you're doing in respect to. And that's it. So notice it's little f here and little f here. All right. In other words, I say down here, in other words, this says that the derivative and integral are inverse operations. Okay, because it's doing the integral, then you do the derivative, and you get back out the same thing, the same function, but with x plugged in. Okay. What else do I say here? Every function, yeah. So these are just different ways to say it. Oh, and the main thing I said here, yeah, it proves that integration and differentiation are inverse operations. So again, we'll try some examples where we actually see it, but the derivative of an integral simply is the function, okay, but with a different variable plugged in. So that they're inverse operations. You get back what you started with. Overall. Now, why is FTC2 useful? Well, to start, I'm going to give us functions that we know the antiderivative of. So we're going to do FTC1, because I want to show you the process, like what it's really doing. But there will be times where we don't know the integral of a function. So like, we'll look down here, like this one. I'm not going to know that integral. And so we can use FTC2 to help us out. A complicated function, yeah, because these processes are inverses, we can use FTC2 to help us out, even if we sometimes don't know the antiderivative. So what I'm going to do here is, again, this will not be the exact what we'll be doing in general, but I want to show you what's happening here, why this works. So what we're going to do is we're going to do FTC1 with the inside part here. Oh, I say it over there, FTC1. Then we're going to do the derivative of it. Okay? And overall, what we're going to do soon is just jump to the final answer here. There's basically no work to these. You're just going to be able to know what the answer is. But for the first one, I want to show you what we would actually do. Any initial questions I can answer? So let me show you what we're going to do. All right, so we're going to calculate the derivative of this integral. Well, what I'm going to do is, since we know the antiderivative here, which we won't normally, let's just see what's going to happen. So first I'm going to do the red part. Block it up there. Okay, so it's we're doing FTC1. So here's a review of that. Capital F of, well, I guess actually it's T. So it's dt. So capital F of T for 3, the antiderivative is 3t. Remember, no c's here. I'll see. So then we're going to do, now here's the thing with this too, is a lot of these integrals for FTC2, you'll see a variable in one of the lower upper limits. So it's not 4 to 6, it's 4 to x, or other variables. So now we're doing f of b minus f of a. So b is the x minus f of a is the 4. Okay, so I'm plugging in x now up there, so it's 3x. Again, this is just FTC1. Minus, then I'm plugging in 4 up here, 3 times 4 is 4. Okay. Now then what this says is d dx. So we're doing the derivative of this. We did the integral, now we're doing the derivative, and you should think to yourself, well, those are inverse operations. We should get the same thing as we started with. And we will. The derivative of 3x minus 12 is 3, which is the exact same we started with. Now, I'll do another one in a second where I'll show you. It's the same thing you started with, but with a variable x plugged in. Okay. Let me ask you this. What if I had changed that lower limit of integration instead of 4 to like 2? What would change for the final answer here? Nothing. That's that right, because 2 would be here, and then f of 2 is 6 instead of 12, but the derivative of 6 is 0. So that's why in the formula up here, it says a to x, where a is a number. It doesn't matter what the number is at all, because when you do the derivative, it's going to be 0. Okay. So it doesn't matter that number. So any number a, up to a variable x. So let's try another one where we see, this time you'll see, it's going to be the same thing but with x plugged in. So let's do b. So I'm just going to do the inside part first. So I'll do an antiderivative of, with respect to t, of cosine t. So that's sine t. Then I'm doing f of b minus f of a, so it's f of x minus f of 4. Or again, any number, wouldn't matter. So I plug that in, it's going to be cosine, oh, no, I'm doing the wrong one, sorry. Sine, going to my antiderivative. Sine of x, we'll plug in x, minus sine, and then plug in 4. Now I'll just pull down d dx. So what we're doing is just doing the derivative with respect to the variable x now. The derivative of sine x is cosine x. And then the derivative of sine of 4, that's a number. So the derivative is 0. So here's an example where, I mean, what happened? Literally, we just plugged in x, right? Like from the beginning to the end, we just plugged in x. It would have been the same here, but there was no spot to plug in x. There's no spot to plug in x. So I think what I'd like to do, let's go ahead and let me do D, and then C and E actually kind of go together a little bit. So let me do D. I'll answer your question, sure.
I'm just wondering, like, what the point is of going through all that if it's just the same answer.
Right. That's why I want to do D. No, you're not. We're not normally going to do this. I'm just showing you why it works.
Gotcha.
Yeah.
Okay.
Just showing you why this is going to work.
Gotcha.
So let me see if I can answer that question right here. Let's go ahead and do D, and then I'll jump back with something on C. D says calculate just using FTC2, and as here we have the integral of a to x, a number up to x. Now here's why we need FTC2. Do we know the integral of that, the antiderivative?
No.
I don't either. Okay, I'm sure there's one out there maybe, but I don't know it. So what we can do though is, since we're doing the derivative, that's important. If we're doing the derivative, we wouldn't have an answer. We're doing the derivative of this integral, and it's an integral a to x. Okay, it's an integral a to x, 2 to x. Okay, so this works. So literally what you said, we're just going to trust that FTC2 will correctly do this. Then we're going to do the derivative of it, and it'll spit back out the final answer with x in it. So here's why this is one step. I'm trusting FTC2. It's just going to be x cubed minus 4 over square root of 1 plus x cubed. So again, what I did there, just trusted that FTC2 was doing some integral, which we don't know, then doing the integral, the derivative, and getting back what we started with.
That's how you do.
Mm-hmm. But the only difference is it will have x, because this was in terms of t, and we saw up here, like in this one, well, derivative with respect to x, and then changes the variable x. So we'll change it to whatever, I know, this one is the upper limit of integration there. Pretty simple. Now I'm going to throw in one thing we're going to see with the next one with chain rule. Okay, but this is literally it. I mean, I could make up. So far, here's what we know: 3 to x, any negative 3 to x. Let's go with that. Of something here, sine of t minus e of t over square root of 1 plus t squared minus 3t. The answer is going to be sine of x minus e to the x over square root of 1. Oh, I'm sorry, if we do the derivative of that integral. It's literally just everything there with x plugged in. So we're trusting FTC2 does the integral, then we do the derivative, get back the original with x plugged in. So it basically boils down to just f of x back up here. You're just whatever the function was, but with x plugged in. Cosine x, 3, that was an x. Okay, so before I start to show you one with a little chain rule, any questions on those? No? So let's see, maybe I should have grouped these a little bit differently. Let's see it with a little chip. I know at the bottom I say this leads us to the FTC with chain rule. I'm kind of doing it with C and E that lead up to it. So let's see what happens here in C. It's the exact same as B, you'll notice. The only difference is I changed it to 3x. So let's see what happens. Everything else is the same up to like the very end, right? So I'm just writing down from B. The antiderivative is sine of t. Then we're going to do f of 3x this time minus f of 4. And so now we plug them in. So it's going to be sine of 3x minus sine of 4. So there's a little difference there. It's 3x instead of x. Okay, and now I'm bringing down from above this. All right, we're doing the derivative with respect to x. The derivative of sine is cosine. So here's where we need a little chain rule. Cosine of 3x, and then what? Times 3. I'm going to put that 3 here. And then the derivative of sine 4 is 0. It's a number. Alright, so notice what happened there. If this isn't just x, you can't just plug it. I mean, here was the original. Let's compare. Cosine t. You can't just plug in x. You have to plug in whatever this is, the upper limit of integration. So you plug in 3x here for t. Then you got to do the derivative of that and put it on the outside.
That's kind of it.
Yes. Now again, we will not normally be doing that. We'll be doing what we did down here, just trusting that it works. So let's do E. It's the same function, cosine t. So let's see if we can do it just by FTC2. So we're going to trust that the function, we're doing the derivative of this integral. All right, so what did we see up here? Well, you plug in the upper limit here, and then do the derivative and put it out front. So it's the same function, cosine, so we're going to do cosine. Plug in x squared, that's the upper limit. and then put the derivative of x squared out front, 2x. And that's the first part. Now I did something different here. Instead of it being a number, I threw in another lower limit that has a variable in it. So let's imagine back up here, it'd be like this. We'd do these f of 3x minus f of 4x. And if we had it, then we'd have to do another term here, minus. And then if we were actually doing the derivative, it'd go back to cosine. And it would have been 4x, but then derivative of 4x is 4. So basically, if this is a number, it becomes 0. If either of those are a number, it becomes 0. If not, there's going to be two terms, subtracting each of them. And you do the same thing for each one. So now since this is a 4x, I'm going to have a minus here. And then I got to plug in 4x here. So it's cosine of 4x. And then I have to do the derivative of 4x and put it out front. Basically there, I just did a FTC2 with chain rule. Again, we won't always know the antiderivative of these, but I'm showing you one where we would. So for this one, you actually could have found the antiderivative, plugged in the values, then done the derivative of this, and gotten these two terms. So let me show. I can now show you what the actual formula is of FTC2 with chain rule. So that's the second part of this. Okay. So part one of this of FTC2 is this: a to x. Just plug in x. Just plug in x to the original function. Second part is, well, what if it's not a to x? What if it's a to x squared or 4x to x squared? It's not a number to x, it's something else. Well, then we're going to have to have chain rule, basically. If it's anything here except a number in either of these, anything except a number or just x, you'll have to do chain rule. Can I go to the next page? Any thoughts on those right now?
It's all you.
Okay, I know a little abstract because you got to trust that the function FTC2 is working it out. So here's just another look at FTC2, but with chain rule. So this says now, well, it's not just a to x. It could be any functions here. It could be like x squared, 4x, what we just saw. So what's going to happen is what we saw there a minute ago. You're going to plug in the function. Let me go back for a second. Like this one, we plug in 3x, but then we did the derivative of 3x right there. That's what this says. F of, meaning you plug in whatever this is, 3x or some number. Then you do the derivative of 3x, or h, whatever that function is. All right, then minus, and I'll go back here, it was this one. So then there's a minus, and then you do the same thing with the other one. So I called this one the lower limit g. You plug in g, and then you do the derivative of g. Here, I put it, oh, I changed it up on yours, didn't I, right here? In other words, okay, I said in other words right here. Another way to think of it is f of b times b prime minus f of a times a prime. I also put here, notice that when you're just doing straight up FTC2, it's little f. It's the same function you started with. It's not an antiderivative. Don't do capital F for this. See, this is where it can be confusing. Capital F is FTC1 to find the area under a curve. Little f is for FTC2. One last thought, and then we'll try these last three, is sometimes students are like, yeah, okay, when do I use FTC1 or FTC2? I'm not going to tell you. I mean, just look for this. Is there a derivative? If it's just a straight integral, it's just a straight integral of that's area under a curve. If it's the derivative, that's the clue right there. we're doing the derivative of an integral, and that's it. That's an inverse operation. So that's the clue right there that says it's FTC2.
So if it has like a capital letter in front of it, like f of x, when f is capital, that's how you know it's like in the example. It's like
Oh, down here?
Yeah.
Like that? Maybe, yeah. Because here, you know what I did on these? I just did, I wrote it a different way. I said, here's a function, find the derivative. So we're finding g prime, so we have to do the derivative d dx of this. So maybe. Okay, so let me show you, this is final FTC2. Meaning, I'm not going to do, I guess on the first two, I could do an antiderivative. We would know those. The third one actually. Okay, wow. Well, you're not always going to know the antiderivative of them. But I'm going to show you what FTC2 is that we'll do here. So let's do this one. So we're doing the derivative of each of these, meaning I'm going to do the derivative of this integral. Here's FTC2 in its final form. It really boils down to what I put up there. F of b prime minus f of a prime. So the integral and then the derivative will inverse operation. So I'm going to get out something that looks like sine t. I start by putting in b. So that's sine of x squared. I'm putting in b, x squared for t. And then whenever you plug the b in, I gotta do b prime. Derivative of x squared is 2x. You can write it after. I just like to not take an extra step. You know what? Hey, let me actually do some of this. So let me write it after for now. And I'll do more stuff. Then it's minus. And now I'm going to plug in a. Now, since a is a number, it's going to be 0. Yeah. So I just want to write it down so I can show it, so you can see it here. But it's going to be a number because it's going to be 0. I'm sorry. So I'm plugging in a. It'd be sine of -2. So then I have to do times the derivative of -2, which is 0. So real quick, just so I can outline this, this is f of b, where above I had f of h of x. Okay, this is b prime. Then minus, this is f of a, and then that's a prime. That's the final form of FTC. You can always do that. This will work. Now, an easier case is if it's just 2 to x, or number x. You can literally just plug in x. Okay, so this one became 0, of course. And this one, I would just put the 2x out front.
Is that a point two?
No. Where? Here?
Negative sign. Yeah, it looks like a negative sign.
Oh, here. No, that's... That looks like a big point.
Hey.
Sorry.
I don't blow my nose.
It happens. It happens.
Yeah. So let's do the next ones. I won't write f of b prime out like that as much, but just so you can see how I more naturally do these. I need some more space, so I'm going to get rid of this one. All right, so on b, here's what we can do. I'm following this form. So I'm doing the derivative, so I'm doing d dx of this integral. That says I got to do FTC2. So here's what I found. I would do f of b. So here's my b, x squared. I'm going to plug in b. So it's -2 x squared minus 2. I'm going to need that in parentheses because it's going to be multiplied by something else. So I just plugged in b. Now I have to do b prime. Here's where, when we do the antiderivative, then the derivative, we need a chain rule. So times the derivative of b, which is 2x. Derivative of x squared. Minus, and I repeat with a. So a is x. So I plug in x here. Now notice it's going to be in parentheses, -2x minus 2. This is, again, where there was already a minus from the formula, but then plugging in x. Alright, and then really times the derivative of x, so this is a prime, which is 1, right? So don't really have to write that. Now this one we can actually simplify a little bit. So I'll distribute the 2x and get negative 4x cubed minus 4x. Over here we can distribute the negative. So we got plus 2x plus 2. And so that combine the middle terms there. So negative 4x cubed and minus 2x plus 2.
Back out of 2.
Oh, you could. I'm just
Nah,
gonna move it. So I want to do a couple of these just so you can get used to the process of this. Again, this is the final, yeah, this is really the final formula for this one. They're the same thing. It's little f. So let's do the last one. I'll see if there's any overall questions. So I'm doing the derivative of g. So this is the derivative of the integral of e dx to tangent x of t squared. Okay, so what I'm doing here is I'm going to plug in b for t. So b is tangent x, so I need a little more room. Okay, so I'm going to plug in b. So I'm plugging in tangent x for t. So it'll be tangent of x squared. Now I'm going to do b prime, the derivative of tangent, which is secant squared x. Yeah, and then I just got to repeat for a. So minus,
You need x squared.
plug in e dx, so this is f of a, plug in a for t. So it's e dx in place of t squared times the derivative of a. The derivative of e dx is e dx. Not much to really simplify for that one, so let's just leave it. That's a nice one, it's just already in the form.
Love it.
So, what can I answer on that right now? Any questions I can answer?
Just gotta trust the process.
Pretty good at the moment.
You see what I mean? Where like later on, you're not going to actually do an antiderivative, and then the derivative. You're just going to trust the process, really. Yeah.
It's just about
Joel and B. That's
It's
his name.
exactly
Is
about
that his motto or something?
Every picture
All of the
he
Sixers,
posts,
yeah.
hashtag trust the process.
The Sixers for a while, like all of them were doing it, but he still didn't.
I like because it took many years for them to do the draft picks and
It was
finally
just
get good again.
Everything.
I like that. Okay. This is the Joel Embiid theorem.
Yeah.
G-J-E-T.
Yeah.
J-E-T.
The Jet. Wow.
Jet. The Jet. Kenny the Jet Smith.
No.
You know about him?
So, so quick overview of what we did. If it is just the integral, usually from a number here, 3 to 6 of a function. Okay, that's FTC1. You actually find an antiderivative, you plug in b and a. Okay, that's FTC1. If it says do the derivative of an integral, and often one of these will have x in it, or really should have x in it, and the derivative of an integral, then you're going to trust the process. Oh, that's t cubed over sine t or something. Where if it's a number, it's just going to be 0. But if it's a variable one, you plug in, like this one, I'd literally plug in x squared for t everywhere. And then you multiply by the derivative of that, derivative of x squared, 2x. You do it again for the number, but the number is going to be 0. So.